Buenas noches.
Good evening, ladies and gentlemen. Welcome to our lecture, part of the series Science at the Cosmos, Science about the Cosmos. As you know, a telescope is like a way to see the universe the way it was before, and we have the oldest light we could get information on, CMB, and we get an idea on the way the universe was 13.5 billion years. We have now the 50th anniversary of its discovery. It is very important to discover the theory of Big Bang without beyond any reasonable doubt, and to make cosmology, which was a part of philosophy before, as part of physics, with figures, because all the details must coincide. And CMB 50 years ago was important. It is very important now, and the primordial universe. And our lecturer today, Associate Professor of Astronomy and Physics, Professor John Kovac, will take us to the frontier, to the border of the discovery of what we're looking and what we're studying and what we're trying to see. So, Professor Kovac, all his career working in cosmology for 25 years, his cosmology research focuses on observations of the cosmic microwave background, polarization of the cosmic microwave background. Not only temperature is important, but light polarization gives us fundamental information. His PhD thesis under the mentorship of Professor Hallström at Chicago University,
la primera detección de esa polarización.
And during his graduate studies at the University of Chicago, supervised by Professor Hallström, the thesis focused on the first detection of CMB polarization in 2002 with a degree angular scale interferometer, the DASI, for which he was awarded the Granger Prize Fellowship. Those differences of temperature are due to quantum fluctuations, mostly, almost for sure, but in sciences we're never sure. But it was during the first fraction of a second, during a process of expansion of the universe, where fluctuations, quantum fluctuations became cosmological, and we can see this with telescopes. And that is why he was awarded the Granger Prize Fellowship, and he kept on at the Caltech for years, working with important fellowships, and under the mentorship of Professor Andrew Ladd, he worked on different polarimeters using quad and bicep 1, and then Professor Kovac has participated at the design of 8 different generations of telescopes. More specifically, he's the leader as Bicep 2, and he will talk about this South Pole, the Bishop and Kirk Array series of experiments. Back in 2011, he got Alfred Sloan Research Award and early career. The Early Career Award also given by the National Health Foundation, and that's given to the best researchers in the US. But what made Dr. Kovac worldwide known is that in 2013, March 2013, they announced Biceps 2, this experiment, with the discovery of patterns, curl patterns in the CMB. That is something astonishing, it's very interesting. Professor will talk about this. And the reason is that, as the inflation theory explained, that there will be temperature differences. Also, they predict a gravitational field will have quantum fluctuations that will predict that there will become gravitational waves that will trigger a given pattern of polarization of CMB. That is the pattern that was described by Bicep 2. And there was a big press conference there. It was on Monday back in Mars, and Friday, all over the world, the scientific community and everywhere, I have never ever seen such a reaction worldwide about it. On Monday, we were all trying to participate at this round table, this press conference, but it wasn't possible. Everything was overloaded and we couldn't have access to it. And I remember that day, I couldn't sleep, because if it was true, if those patterns were due to the gravitational effect, this is an incredible discovery and one of the milestones in sciences with lots of huge implications. So then later we saw there was a contamination of galactic dust. We knew it was there, and it was very difficult. I had been working to analyze this and to delete the effect, but the contamination was bigger than what was estimated at the beginning. And then we'll still have this enormous challenge with lots of tests and experiences, trying to disclose, trying to look for this radiation, how to delete the effect of the contamination in order to confirm if the signal is there and the size of the signal, because this will allow us to understand in a better way physics. That's what we would like to know. So Professor will have lots of things to tell us. I haven't mentioned that Professor comes from Harvard, and he is a professor, associate professor at the university. He needs no introduction. And I'd like to mention regarding Professor Kovac, not only his research, that's fantastic, but also his pedagogical efforts. In Harvard University, he has a lab of advanced astrophysics. And there, the lab students are learning, are designing, are hands-on, constructing antenna. This antenna is to measure CMB, and I think it's extremely difficult. But we did coincide once at a dinner party where people were admiring him and say, "Are students doing this? Is this visible? That's incredible." So he's a very special person, a great professor, a dear friend, and he needs no introduction. So what he's going to tell us is fascinating. And let's start now. And the floor is to Professor Kovac. You have the floor, sir. Thank you.
Can you all hear me okay? Well, first, thank you for that very kind introduction. That was really wonderful. And I'd like to thank the Fundación BBVA for giving me the honor of being able to speak here today. And I'd like to thank all of you for coming tonight. It's wonderful to see so many people here, and I hope you'll enjoy this talk. I'll be speaking tonight about the oldest light in the universe, and I'll be talking about the effort to study it with extraordinary telescopes. These telescopes are at the South Pole, the very end of the Earth. And I wanted to begin by showing you something that I at least think is extraordinarily beautiful, and I can promise you it's something that very few people actually get to see in person. So this is what the South Pole looks like by daylight. If I could ask, maybe we could bring the house lights down now. Thank you. This is still what the South Pole looks like in daylight. When most of our team goes to the South Pole, when the temperatures are warm enough to get in and out of this place. And you can see here on the horizon the array of telescopes that we have built there, me and many other researchers over the last 20 years as we've developed it as a place to do astronomy, to study the early universe. But at the end of the very short summer season, most of us get on an airplane and leave. And then a few brave souls stay there for a long 9-month winter season, and the sun goes down in March, and it won't come up again for another 6 months. And you can see the place becomes very otherworldly. You can see the observatory buildings in the foreground and the night sky above, The air, the coldest on Earth, minus 70 C or below, is also the driest. It's nearly transparent to the microwave light that our telescopes observe. So overhead in these sped up videos, you can see the galaxy turning like a pinwheel above a spot that's fixed above our heads. You could see some flashes from satellites. The aurora in this picture here is visible to our eyes, but invisible to our microwave telescopes. This last video was one that was shot by our two winter-over scientists who are operating our current telescopes, the Keck Array and Bicep 3 at the South Pole. They're with a winter-over crew down there of about 45 people, and they're awaiting the sunrise, which will happen 10 days from now. And they hope that the data that they've been collecting during this 9 months of isolation in this year will help to unlock some of the mysteries of cosmology. It's quite a sacrifice and quite an adventure. So we actually have a very successful model right now of cosmology. It's a beautiful model that explains how the universe that we see around us now, the stars and galaxies that we're familiar with, evolved through the 14 billion year or so history of the universe. After the first stars and galaxies formed just a few 100 million years into the history of the universe, and looking even further back, how the first light was emitted when the universe was much smoother, much smaller and denser than it is right now. We know more about the universe at this period when it was 380,000 years old than perhaps at any other epoch, including the current epoch, because we've had the microwave background radiation to use as a tool to study this part of the universe's history in exquisite detail. So I'm going to make a theme of my talk tonight, the fact that in cosmology we have many pictures that currently are very beautiful and fit together with the data in many ways, but that also leave many fundamental gaps, many mysteries that are completely unexplored, that need explaining, and presents fascinating challenges at the frontiers of cosmology for measurement and for progress on these fundamental questions. So to see how we got to this picture, and this talk will focus primarily on the earliest stages of this picture, the very early universe, and how the conditions of the very early universe arose, I'm going to back up a little bit and talk about history for a few slides. So modern cosmology, in a nutshell, begins with Albert Einstein 100 years ago this year. In 1915, with the realization that space is curved by gravity. Now, this was not initially a cosmological insight, but very soon afterwards, the realization dawned on researchers, and Einstein himself took some convincing on this point, that his theory of general relativity implied a dynamic universe, a universe that is evolving in space. And indeed, in the 1920s, we had observational evidence that was largely collected by Hubble and others and interpreted accurately by Georges Lemaitre, that the universe that we live in is apparently expanding. The redshifts of galaxies can be interpreted as all of space growing larger. Now, there are multiple ways of interpreting the implications of this, but a natural one is to imagine that you can take that expansion and run it backwards in time. And ask, does that mean that the universe was once much smaller, much denser? And if it was, then it must have been hot and dense, perhaps like the inside of the sun. And in the 1940s, researchers following up on the implications of this realized that they could explain the abundances of light elements, hydrogen and helium, in the universe by imagining the nuclear reactions that would occur in the early universe. But if the universe had a hot and dense beginning, then perhaps you can still see the glow. And the realization that this may be possible was something that was dawning on people in the 1960s, almost simultaneous with the actual discovery of this glow, the cosmic microwave background. So the cosmic microwave background is the oldest light that we can see. If we look out from our present day situation in the universe as far as we can with our telescopes, of course we're looking back in time, and eventually we look nearly 14 billion light years away, past the formation of the first galaxies, to the very early universe, and there we hit a wall. We see a fiery wall because the universe at that very early time was dense enough and hot enough that its constituents, primarily electrons and protons, formed a hot ionized plasma. The charged particles were dissociated and were very effective at bouncing photons, particles of light, around. The photons would ricochet off these charged particles, making the universe opaque to light. If we run the history forward then, from this early time, the universe expands and cools, and then at a very brief moment in the universe's history, it undergoes a transition, much like a cloud dissolving, where it's no longer hot enough to keep that plasma ionized, and you have the formation of neutral atomic hydrogen, and the universe becomes transparent. And the light that pervades the universe travels in straight lines, and some of it has traveled across the entire distance of the universe to be reached by our telescopes. And that is the light that we study with these microwave telescopes, the oldest light. It was emitted when the universe was a temperature of around 3,000 degrees Kelvin. But because the universe has stretched out and expanded by a factor of 1,000 since then, its present-day effective temperature is a mere 3 degrees above absolute zero. It's a very faint microwave light, not visible with the naked eyes, and that's why we need specialized microwave telescopes to see it. And the first telescope that did see it is pictured here, the discovery of the cosmic microwave background by Arno Penzias and Robert Wilson was made with the 20-foot Bell Labs antenna in New Jersey. In 1964, they announced it in 1965, so we're celebrating the 50th anniversary of this, as Anna said. They received a Nobel Prize for this in 1978, but more importantly, this discovery was really the smoking gun evidence that the universe did have this history, that the hot Big Bang was the correct model of the history of our universe. And this had an enormous impact on cosmology. It basically established cosmology as a credible science, allowed us to work hard to refine measurements, particularly of this microwave radiation, to study the history of the universe itself. And we've been doing that for the last 50 years. So moving very quickly over the first 35 years or so of that arduous history, the microwave radiation was studied in greater and greater detail as telescopes became more and more powerful. And in 1992, the Kobe satellite first detected ripples, fluctuations in this microwave radiation. And within 10 years, that radiation had been mapped out so that those fluctuations were understood in great detail. So this plot here, from a little over 10 years ago, is not the best plot of its kind. The Planck satellite has now made exquisitely detailed measurements of this same thing. But I want to use it as an illustration, first of a kind of plot that I'm going to show several times in this talk, and of how far we had come a little over 10 years ago, almost 15 years ago, in this field, studying the cosmic microwave background. So what we see on this plot are the statistics of the maps that we make. And you can see some of those early maps of the fluctuations in the temperature of the cosmic microwave background. And we plot how strong those fluctuations are as a function of angular scale. Angular scales on the sky of 1 degree, about twice the size of the full moon, are shown here on this axis where this number, L, equals around 200. And that's where there is this sharp peak in this map. Larger angular scales are shown here at lower L numbers, and angular scales smaller than a degree are shown here at higher L numbers. And we see there is this sharp peak, and Theoretically, we expect there to be such a peak from our understanding of the physics that happens during that first 380,000 years in that hot ionized plasma. We understand that sound waves will propagate in that hot ionized plasma and will produce a fundamental tone if those sound waves are excited by density fluctuations all at once, all at the same time, coincident with the initial Big Bang itself. And the details of those sound waves and the overtones that we measure will depend on the constituents of the universe, its composition. These acoustic oscillations in the cosmic microwave background were, I think, probably first predicted by Jim Peebles, who I understand gave a lecture in this series just this year. What I'd like to illustrate here is that the measurements of these statistics from the WMAP satellite and from these ground-based telescopes, many of them in Antarctica and at the South Pole, were already very precise over 10 years ago, and we're in excellent agreement with this red line, which is a theoretical prediction, which depends on model parameters that describe what the universe is made of, and they describe the initial conditions, the density fluctuations that started off these sound waves. So here's another kind of plot, the second kind of plot that I'm going to show different varieties of in this talk. This is a different way of analyzing the information we can get out of such a graph as the one that I showed you on the last slide. Here we are looking at theoretical parameters of those models, like that red line that was on the previous plot, and how they match up against the measurements, against the data. And you can see different kinds of data sets here depicted as ovals on this plot. The model parameters on this axis are the density of matter in the universe compared to the critical density, and the density of so-called dark energy in the universe that's driving accelerated expansion of the universe. And different points in this plane represent different values of those two parameters, and how well they match up against the data sets are indicated by whether they fall within these ovals or not. The smallest oval is the best agreement, and the other ovals indicate progressively worse agreement. And you can see that the CMB is good at constraining a combination of these two parameters, but there is a degeneracy here. And these other kinds of measurements from different cosmological probes, including supernovae and surveys of galaxies, constrain different combinations. But the remarkable thing is that all of these ellipses overlap in one spot, indicating a consistency between all of our measurements. You can take any two of these and see where they intersect, and you see the third one matches. And moreover, there is a line on this plot which indicates special models. Those are the models where if you add up the dark energy and the matter in the universe, they equal the critical density that's needed to make the universe flat. And you can see that that is also a good agreement with the data. So we could have taken this class of models here, that line, combine it with the measurements from CMB to make a prediction for the matter density and the dark energy density, and see that it was consistent with what we see from supernovae or from galaxy surveys. It's a concordance of cosmology. So now if we plot that information about the constituents of the universe in what may be a more familiar form, this so-called cosmic pie or cosmic pizza, we see what the universe's makeup is in different fractional terms. Only 5% or so of the universe is in ordinary matter. And of order 30% of the universe is in dark matter and 65% in dark energy. The modern numbers on this composition have changed by a few percent, but I like this slide because this was a slide that we were able to make almost 15 years ago. This was actually before we had even data from the WMAP satellite, that beautiful data set. So the universe was already starting to reveal this picture, the standard model of cosmology at that time. And although it's a beautiful picture, and it's very concordant, we must be humbled by the fact that most of the universe is made up of dark matter and dark energy, things that we have only names for, but we don't understand. So there's a lot of work to be done here in understanding even the composition of our universe in this concordance cosmology. So this is a strange group But the universe is also flat to at least 1%, and it's smooth to a much higher degree than that. So this is consistent, as you'll see in the next few slides, with predictions from inflation. So can the model of inflation, the model of the initial conditions of the universe that we'll be talking about today, also explain where structures came from, where those initial density fluctuations that started off those acoustic oscillations, where they arose? It's very important because those density fluctuations evolve to form all the structure in the universe today. So just to reiterate some of the incompleteness of our standard view of cosmology, although it's a wonderful and coherent description of the universe we observe, it has conceptual holes, mysteries that are not explained by the standard model. The smoothness of the universe that we observe, the fact that when we look out at different spots in the cosmic microwave background, we're able to measure the same temperature to very high precision, to within 1 part in 100,000. And yet, we know that at 380,000 years into the history of the universe, when that light was emitted from those distant parts of the universe, they were much more distant than 380,000 light years from each other. Light would have had no way of traveling in the standard model of cosmology between those different patches. No way for causal physics to explain how the universe could have all acquired the same temperature unless it was just defined that way, which is not a very satisfying explanation. We would like a dynamical explanation, a causal explanation for how the universe got to look that way. Likewise, the universe that we observe now is exceedingly flat, and that is an unstable state. As the universe expands, any departures from flatness will rapidly grow. It's like finding a pencil that's balanced on its point. It needs to be very, very precisely balanced on its point for it to remain there for any period of time. And yet we know the universe has expanded tremendously, and it still is very flat. So how is that possible? How is it possible to find the flatness of the universe? Relic abundances. So we know that if the universe began in a very high energy state, we would expect all kinds of exotic artifacts of high energy physics, things like magnetic monopoles, to be common, and yet we don't observe such things. So how is it possible that those things were removed from the observable universe, or diluted to the point that we hardly ever see them? And how can we understand the origin of the small ripples that we do see in the universe now? Well, the theory of inflation purports to explain these mysteries of the initial conditions of the standard model of cosmology. And it does so by saying in the first fraction of a second, the universe underwent an expansion that was not merely fast, but it was exponentially fast. So there was a characteristic doubling time to the universe's size. So we're at a foundation sponsored by a bank, and so an example of exponential growth that's familiar to all of us is compound interest. We know that if we have money earning a given rate of return, that there'll be a certain amount of time that it takes for that money to double. And if we're fortunate, we may experience several such doublings in our lifetime, and our savings grows. If the rate of return was very rapid, we would experience many such doublings, and we would become astronomically rich. So the theory of inflation says that there was a doubling time for the expansion size of the universe in the first trillionth of a trillionth of a trillionth of a second that was actually much smaller still, a fraction of that. The universe doubled and doubled again, and it doubled many, many times in size. And in that mind-bogglingly expansive growth, the universe was stretched so that the unevenness was smoothed out by the stretching. And the crinkles, departures from flatness, was also smoothed out. Any exotica from high-energy physics were diluted to an almost unobservable density. So the relic abundance of these exotic particles was resolved by this rapid expansion. But most importantly, inflation gives us a way of understanding how the structure in the universe arose. And it explains it by saying that quantum mechanics is responsible for the origin of the structure that we see, the origin of those density fluctuations. So how does this work? How is this possible? So I'll make a brief digression to talk not about the early universe, but about black holes. And in the 1970s, Stephen Hawking, who I'm sure is known to all of you, did important fundamental theoretical work on how quantum mechanics acts in the highly curved space around a black hole, and particularly around the event horizon of a black hole. So we understand that quantum mechanics tells us that space is constantly seething with uncertainty that can be thought of as the continual creation and annihilation of virtual particles that we never actually observe physically. But we know that they're there because they effectively mediate the forces of nature. They give us the laws of physics as we understand them. But they're generally not classically observable. But that situation changes when you have highly curved space-time like around a black hole where there exists an event horizon, a point of no return, where you can have two observers close to each other, one of them cross the event horizon and one of them not, and the curvature of space prevents them from ever seeing each other again, from contacting each other again. And if you have virtual particles that experience this effect, across the event horizon, quantum fluctuations become unresolved. You can think of this as particle pairs, one falling into that black hole and one exiting the black hole. And this phenomenon is called Hawking radiation. So we believe that this really happens with black holes. So why am I telling you this story? What does it have to do with inflation or with the early universe? Well, in an exponentially expanding space, you actually do have an event horizon. So let me try to illustrate this with an example. Bear with me. So although the exponential expansion that's posited by inflation is extremely rapid, the doubling times are tiny. And the scales involved, the distances, are also tiny, very small. The observable universe starts off with a size less than the volume of a proton. I'm going to illustrate this example by a game of soccer that we might play. I know that soccer is a popular sport here in Spain. So if we were playing soccer, kicking a ball back and forth, and we started off at a distance from each other of 2 meters, and every second the universe doubled in size. If we were both at rest in the universe, the space between us would double with each second. And we would kick and the space would be 2 meters, and then the next second 4 meters, and you have to kick a bit harder to get the ball there within the next second at 8 meters, 16 meters. The game becomes more and more strenuous. But if you run this forward, you realize that in less than half a minute, the space between us in each second is growing faster than the speed of light. And the speed of light is a fundamental limit to how fast anything, a photon or a soccer ball, could in principle go. So the game would end. And in fact, we wouldn't even be able to talk about who we thought kicked better until the universe were to stop exponentially expanding, and at some much later time, at a more leisurely rate of expansion, maybe we would come into touch again. We could resume the game. But during this period of exponential expansion, there is really an event horizon in that exponentially expanding universe. We lose causal contact with each other. And quantum mechanics says that this same mechanism of Hawking radiation will freeze quantum fluctuations across the horizon scale, making them real, freezing them into the fabric of space-time. And the equations, these are, I think, the only equations in my talk, for the characteristic temperature of a black hole, that is, the strength of the fluctuations, the quantum fluctuations that you see radiating from a black hole, depends on the event horizon scale, the Schwarzschild radius of that black hole, for those of you who are familiar with that term. In an inflating universe, the equation looks almost the same. The strength of the fluctuations that are laid down in an inflating universe is related only to the event horizon scale, the horizon scale of that exponentially expanding universe, which is linked to the energy that's driving inflation, generally thought to be a very, very high energy indeed, or equivalently to how early in the first fraction of a second inflation occurred. So observations show that primordial fluctuations actually match the features expected for such quantum mechanical effect to great detail. They have simple statistics, so-called Gaussian statistics. They're almost scale invariant, but we now know that they even have a slightly tilted spectrum, a departure from being scale invariant. That means that the fluctuations that we observe on the largest scales are slightly stronger than the fluctuations we observe on small scales. And that's just as you might expect in inflation. If inflation is happening at an energy, or equivalently at a horizon scale that is slowly rolling to an end, because inflation has to end if we are to experience the rest of the history of the hot Big Bang as we understand it. So it's a beautiful theory. It's a very compelling theory. But wait, inflation is crazy. I mean, come on. It's talking about physics at energy scales that are 10 orders of magnitude beyond any that we can probe with experiments that we can construct in accelerators on Earth, at CERN, say. And it requires new physics. It requires the invention of something that we just call the inflaton, for lack of any better knowledge about it. And we don't know what form that takes. We don't know what that physics looks like. It relies on the marriage of quantum mechanics in the strong gravity regime. And although I told you a story about how that works, this is really not something that we have direct experimental evidence of. And moreover, quantum mechanics and general relativity are two theories that we have not been able to fully reconcile theoretically up until this point. We don't know how they fit together in detail. Even more controversially, some forms of inflation can lead to consequences like it appearing that it's inevitable that we have a generation not just of our universe, but of an infinity of universes, so-called multiverses. Not all versions of inflation suffer from this issue, but this is certainly something that is commonly debated, and it bothers many people. The fact that having an infinity of possibilities may mean the end of predictive physics, sort of throwing up our hands. And does it really do the job of helping to explain the initial conditions in terms of something that was simpler than those mysteries that we started out with? That in itself is something that is a subject of great debate. So it must be recognized that all of these mysteries are raised by the idea of inflation, and yet that's also what makes it so compelling and so worth studying, because these are very deep mysteries. And inflation does appear to fit beautifully with the universe that we observe. So given the situation, as an experimentalist, of course, I ask, how can we test it? What can we do? And so to describe how we're going to test it, I'll show you this picture again. So the modern universe here, going backwards in time, we're able to look back and see this surface of the cosmic microwave background. That's as far back as light can go, when neutral hydrogen formed and the universe became transparent. And these earlier periods, the formation of the universe, when nuclear physics happens, when fundamental particles form, all the way back to what we postulate as inflation, is not directly observable by this light. But inflation tells us that there are at least two types of quantum fluctuations that are generated. The density fluctuations that I've told you about so far, and also quantum fluctuations of the gravitational field itself, would show up as gravitational waves. And those waves would propagate from this early time through the universe, through this first 380,000 years of its history. And they would be present in the universe when the CMB is generated. So although visible light stops here and the rest of the universe is dark except by inference to visible light. These gravitational waves may provide a messenger directly from inflation to this time when the CMB was released, and we'll see that they may imprint in the cosmic microwave background a characteristic pattern in its polarization. So, I haven't talked yet about the polarization of the cosmic microwave background. The background radiation was first predicted to be polarized by Martin Rees in 1968, and I understand Sir Martin was another one of the speakers in this lecture series. It's a very impressive series that you have. I'm humbled to be here. So the mechanism for generating this CMB polarization is the scattering, the last scattering that happens of these photons before the universe becomes neutral and transparent. And you can think of these photons as scattering off charged particles, usually off charged electrons. And those photons are coming from all different directions in this hot ionized plasma. But if there's a density wave in this hot ionized plasma, the strength of these photons is not equal. You see stronger photons coming from the left and the right, weaker from above and below. And so what that does is it sets up a difference in the way that that electron, that charged particle, is being vibrated by the fields, the electric field and magnetic field of that light. So the electron responds to the electric field of that light coming in from the left and the right where it's stronger, and it vibrates preferentially in the vertical plane. And that means that when it scatters away from the screen here towards you, the present-day observer with your CMB telescope, it will have a slightly stronger fluctuation in the vertical plane than in the horizontal plane, where the light that's exciting it is weaker. So I've exaggerated this effect here. The red might typically be stronger than the blue here by only 1 part in a million in the CMB itself. But this is enough to produce a characteristic polarization that is linked to these density waves. And as I move my electron across a density wave that looks like this, that has this kind of pattern, I would get this kind of pattern in polarization. First vertical, as I described, and then as I move half a wavelength over here, horizontal, and then vertical again. This kind of pattern is what we call an E-mode polarization pattern. So if I want a pattern of polarization that has polarization aligned not vertical or horizontal with this wave, but at an angle to it, I can't do that with a density wave. There's no way that I could orient this density wave to produce a pattern that looks like this. I need something else, a different direction in the problem to pick out the diagonals here. And a way I can do that is with a gravitational wave. It's different physics. A gravitational wave describes transverse compression and stretching of space-time as that gravitational wave passes through space. And if that is happening 380,000 years into the history of the universe, when the CMB is being released, that would cause the light to be stronger on one axis and weaker in the other, and would set up polarization, much as before. But I can orient the gravitational wave such that the compression and the expansion of that gravitational wave lie at an angle to the direction that that gravitational wave is modulated. And so I can get a pattern that looks like this B-mode polarization pattern from the gravitational wave. There's no way of getting that from these density waves. And that's what makes patterns like this so useful, so essential for studying very faint effects that would otherwise be swamped by these much stronger density waves in the early universe. So if I take these very artificial single waves and I superimpose many of them, and I do so randomly, say, as happens in the early universe, with random quantum fluctuations, I will get characteristic patterns by a superposition of E-modes that look like this. They're radial patterns, sometimes outward, sometimes tangential patterns around, but never swirling patterns. You never get a pattern that has curl to it mathematically. B-mode patterns have these characteristic pinwheels. They look like they have a swirling pattern. Okay, so this is another plot of a power spectrum of the cosmic microwave background. And here you see the temperature spectrum that I showed you before. And here you see just how much fainter the polarization amplitude is The E-mode polarization here is the dominant form of polarization because it arises from the much stronger density fluctuations. And I should mention at this point that the CMB light, as it travels to us from the early universe, is not completely undisturbed. It's bent slightly by gravitational lensing. Again, one of Einstein's predictions, by all of the matter between us and the surface of last scattering of the cosmic microwave background. All of the mass in the universe will deflect that light on average a couple of arc minutes one way, a couple of arc minutes another. It's a very small deflection, but it's enough to convert a pattern that had no B modes, no swirling to it at all, to one that has a very small amount of swirling. And that is what this spectrum here is. The lensing B mode spectrum is derived from this E mode spectrum with gravitational lensing. Inflationary gravitational waves, if they are there, will peak at angular scales of a few degrees here on the sky, and they will have this swirling pattern on those larger angular scales. But the amplitude is unknown. The amplitude depends on the strength of these quantum fluctuations, which in turn depends on the energy scale of inflation. And you can build models of inflation at any energy scale. So we don't know at what level to expect these gravitational waves, but we want to look for them and see at what level we might find them. So there are other sources of microwave light that can produce both E modes and B modes and galactic foregrounds. The emission from our own galaxy is the most important to worry about, because here usually the galactic magnetic field plays the role of introducing another direction to the problem that allows the creation of swirling patterns and B modes as well as E modes. And the information that we had on the polarized emission from our galaxy that might get in the way of these observations before the beautiful data that we had from the Planck satellite was relatively limited. So the WMAP satellite, the previous CMB satellite mission, gave us low-frequency maps of what the radio emission from our galaxy looked like in polarization. This is so-called synchrotron emission, electrons spiraling in galactic magnetic fields. So limited in sensitivity, but nonetheless useful polarized maps. Dust emission, however, had not been mapped out in polarization, not in the faint regions of the galaxy where we want to train our telescopes to have the cleanest parts of the sky. So there we have to use models to extrapolate what was known about the polarization of dust in our galaxy from bright regions to the very faint regions. Okay, so how do we make the measurements that we make with our telescopes? Well, first, of course, we have to get to the South Pole. And that's actually not so hard these days. You fly to Christchurch, New Zealand, and from there you fly on military planes, first to the coast of Antarctica in McMurdo, and then here to South Pole Station, about 800 miles in the interior. And on the coast of Antarctica, things look much like you might picture. There are beautiful mountains and glaciers. If you're lucky, there might be penguins. But you're rushed through there. You only spend a day or two before they trundle you off to the South Pole. And that is an unreal place. It is like being on another planet, except for the buildings that have been built there. If you turn your back on those and look in the other direction, you realize just how barren this wasteland is, featureless out to the horizon. So we fly there on these big ski-equipped C-130 military aircraft, and this is how our telescopes get to the South Pole. They come out the back of these planes. And how we get to the South Pole, we come out of the front of the same planes. And we've been going to the South Pole because of the extraordinary dryness of the atmosphere for many years now. So we first tried to do observations of the cosmic microwave background during the winter time at the South Pole just over 20 years ago. And it was a first effort, and we weren't very good at it. The telescopes were entirely out in the cold, and you can see here the winter over operator of the telescope lifting liquid helium to cool the telescope up to the platform where the telescope is. And here's what the telescope looks like on the inside. So this was a very hard way to work. I know this because this was my job. That was me 20 years ago. And we learned essentially how not to design these telescopes. We got much better at it as the years went on, and as Anna mentioned in her introduction, in 2002, we had a telescope where the insides of the telescope were all heated and easy to service, and this was a telescope that had remarkable technology in it. It first achieved the sensitivity to detect the E-mode polarization of the CMB in 2002. It made this map, and now on this map, the color scale indicates the temperature fluctuations. But these lines here on this map indicate the polarization. That is, the fractional degree that you will see photons oriented with an electric field more in one direction than in another. The direction of that line indicates the orientation, and the length of the line indicates the strength. And the strengths are very small here. You can see this is 5 millionths of a degree. So these polarization departures are about 1 part in a million. So for every million photons we get coming in with one orientation, we might have 1,000,001 on average coming in with the opposite orientation. Telescopes have to be exquisitely sensitive to make that kind of measurement. So this was big news, but it was ultimately just confirming the physics that we believed had to be there according to the standard model of cosmology, which was already pretty well established by then. The exciting thing for all of us working in the field was the prospect of using polarization as a tool for new physics, to search for the B-mode polarization that might be there from gravitational waves. And here I'm showing you the spectrum that might arise in B-mode polarization from gravitational waves at different levels, where this number R here is a parameter that describes the ratio of the strength of gravitational waves to density fluctuations. And these different lines correspond to different energies of inflation, different models of inflation that could be built. And for a decade, we were just building more and more sensitive telescopes, but setting upper limits, not getting into an interesting regime yet of constraining the B-mode polarization. So these data points represent only maximum possible levels, but not detections of any B-mode signal on the microwave sky. So if you really want to build a telescope that is optimized for this goal, a good strategy, the strategy that we pursued, was to build a small telescope, one that has the minimum aperture needed to resolve these degree scale structures, and to go as deep as possible into a clean patch of sky. To use a good observing site like the South Pole to get lots and lots of data, many months of integration with many, many detectors. And so this is what the BICEP 2 telescope looks like. It's typical of the series of telescopes we currently run. It has a very simple optical system, just 2 lenses, very much like Galileo's or Newton's early telescopes would have looked like, except that the entire telescope is cooled to 4 degrees above absolute zero. And the focal plane of that telescope here is very large, capable of collecting lots of microwave radiation, and it's kept at 1/4 of a degree above absolute zero. So it's important to pack as many detectors as possible into these experiments, because the detectors themselves have now reached a level of sophistication where their sensitivity is limited by the fundamental quantum limits of the photons that they're observing. The only way of doing better is having more detectors to scale up these experiments. And so the name of the game in making more sensitive experiments has been increasing the detector count. And starting with BICEP 1, 2006 to 2008, where we had around 100 detectors, using technology to assemble those detectors very much like what was flown on the Planck satellite. We switched to a new technology with BICEP 2 and the Keck array that allowed us to dramatically increase the detector count. The Keck array followed BICEP 2, starting in 2011, and it was just multiple copies of the BICEP 2 telescope. We'll see some results from that in a few slides that followed on with BICEP 2. The Keck array is still operating, and just this past year at South Pole, we deployed BICEP 3, which is a new, much more powerful telescope, but again, a small telescope, only about twice as big in size, but has 5 times as many detectors. So it has as many detectors in one telescope as all of the Keck array has among its 5 telescopes. And the next step to come, of course, will be BICEP 4, which will be an array of BICEP 3-like telescopes, and that's what we'll be working on for the next few years. So that's what our program looks like. So I've got to spend one slide at least showing you some of the amazing technology that fuels our telescopes. And this is similar to technology that works in most of the telescopes in this field now, that's enabling us to scale up the number of detectors and the sensitivity. We're able to now mass produce these microwave detectors by patterning them on silicon wafers, not unlike CCD chips that might be used for optical cameras, but we're making microwave cameras here. So we have silicon wafers that consist of, by optical standards, a very small number of pixels. Only a few hundred in this focal plane, 500 in this focal plane. But each one of these pixels actually has an imaging optic built into it in the form of a network of antennas that are summed coherently, so that they form a beam. They focus the light coming into the telescope onto these detectors here. The horizontal light is focused by slot antennas onto one of these detectors, the vertical polarized light onto another one of the detectors. These detectors themselves are superconducting and rely on superconducting readout electronics as well. So very high technology in these focal planes, but technology that can be mass-produced by photolithographic techniques, so that it can be scaled up. And so around 2010, we put BICEP 2 together in a clean room at Pol. You can see somebody in a parka here and a graduate student. This note says, "Please do not feed the graduate students." It's taped to the outside of the clean room as he's putting together the focal plane. There's the BICEP telescope going in through the hole in the top of the building. And what these telescopes do as they collect microwave light is actually very boring. They go back and forth on a patch of sky relentlessly. And it's a relatively small patch of sky, about 2% of the sky. Back and forth, back and forth. They pause to do a little calibration, and they do that for months or years on end. And if things work well, our winter over telescope operator has little to do. He can sit back and enjoy the sunset, very briefly, and then prepare for a long and beautiful night. And the data that we take from these telescopes comes in over the course of the 3 years that we collected microwave light with BICEP 2. You can see the sensitivity of the map integrating down across 2010, 2011, 2012, and the maps themselves are forming up here. Here on the left, we see the polarized maps, the signal that is emerging, that is dominated by the E-mode polarization of the CMB. And here on the right, we see a map that is formed by taking the data set and splitting it in half and subtracting it, folding it back on itself, a so-called jackknife test. And we do that with the data in many, many different ways, so that we can confirm that when we subtract the data in a way that should remove the sky signal, there is no false signal here in excess of what we expect to be the noise, the random fluctuations that come from the measurement itself. And you can see the level of the noise, of the random fluctuations, is very low compared to the signal that we've measured at the end of those 3 years. So looking at this as a polarization map now, the total polarization is dominated by an E-mode signal. If I take only the curling part of that polarization map, separate the E-modes out mathematically and show you only the B-mode part of this map, it looks like this. You can't see it. It's tiny. So I have to blow up the color scale. And now we're finally looking at polarization vectors that are not 1 part in a million, but 1 part in 30 million. You measure the strength of these things in tens or hundreds of nanokelvin, that is billionths of a degree. Extremely faint and challenging radiation to map. Here it is coloring in to draw your eye to the swirling patterns of the B-mode polarization. And this was the fundamental measurement, the map that BICEP 2 produced at the end of 3 years. And this was a B-mode signal that was stronger than we were expecting. Here is what that signal looks like on a plot of the angular power spectrum. So this is the expected B modes that come just from the lensing of the CMB, here on that solid red line. We have a clear detection in these black points here of something above that. The extent of these lines indicates the uncertainty. So there is a very significant detection of something beyond what we expect just from lensing. What is it? After many years of work, we feel we ruled out a false signal from our telescope, from systematics, from contamination that comes from the instrument. So emission from our galaxy, when we announced this result in March of last year, also appeared to be unlikely to at least produce most of the signal. And the reason why we concluded that is that the synchrotron maps, the radio maps that we had, didn't correlate with the pattern that we saw at all. There was no comparison between those maps. And the projections of how bright the polarized dust ought to be were low compared to the size of the signal that we saw. And we were also able to have some weak evidence of the nature of the signal, whether it looked more like CMB or more like dust, from a little bit of evidence that we had at a different frequency. And I should emphasize here again that galactic foregrounds have a different color composition. They have a different brightness as a function of frequency compared to the CMB. And so having different colors is the key to being able to separate these effects. We did not have much information from other frequencies at this time. We were able to say the data were well fit to this theoretical curve here of R equal to 0.2, which is a large value of R. But the true value is expected to shift lower depending on the foreground level. And if foregrounds are indeed a small fraction, we wouldn't expect a big shift. So the most likely interpretation we offered was that this is evidence for inflationary gravitational waves. Okay, so it's been quite a year. Developments of the past year. There was intense media and science community interest, I think far in excess of what we expected when we released our results. As Anna said, our website crashed immediately. We were expecting there to be a few hundred scientists tuning in, and not the whole world. And that brought with it lots of scrutiny of the B-mode measurements themselves, their statistics, the treatment of systematics. And I'm happy to say so far they have held up very well. In fact, they've been confirmed with the new measurements from the Keck array in the last year. But the key issue here is the interpretation of this B-mode pattern. Gravitational waves versus galactic foregrounds. So early worries about synchrotron contamination, voiced by many people, I'd say we're now satisfied that it looks okay. Synchrotron is not playing a significant role here. But persistent concerns about dust, voiced immediately when we released our results by the Planck collaboration, leaders of which said, this looks very exciting, but before we can be certain of the interpretation, we'll need to see what Planck has to say about the polarized dust. That was something that I think we didn't disagree with. This question of could it all be dust was really the key question, and as we began to get hints from the Planck satellite of what they had learned about the polarized dust, it became more and more apparent that this was the key question, and more data would be needed to answer it. And so we embarked on a joint analysis between our team and the Planck team, begun last summer and concluded early this year. So to set the frame for that again, a little bit to show you where we were before that joint analysis, this is what the data that we had in early 2014 looked like. And again, this is another plot of model parameters versus their consistency with the data. And in this case, the model parameter plotted here is the strength of inflationary gravitational waves, R, where 0 points along this axis here represent models with no inflationary gravitational waves. And on this axis here, we're plotting the amplitude of the dust, the brightness of the dust. So points along this line are trading off brighter dust or brighter inflationary gravitational waves. And you can see that the data that we had in 2014 was not very good at distinguishing between the two. It was very good at saying that we had definitely detected, with a probability of 1 part in a million or better, that there were excess B modes, but not good at distinguishing whether those were dust or CMB. It did weakly favor CMB, and the models that had 0 for R were disfavored, but only at about 1 in 10 odds, so not very significant. But the models that we had of the dust brightness at that time all indicated best guesses at the dust brightness that were quite low. They were different from each other, but they were all quite consistent with what the data seemed to prefer, these low values of dust that would leave an excess of inflationary gravitational waves. And so that was the basis for the conclusions that we drew last March. And when the new Planck information showed us that those models of polarized dust were looking unreliable, it was evident that we needed better data to be able to distinguish between the possibility of all dust or a combination of dust and CMB. So that data came from the beautiful Planck satellite that mapped the microwave sky at 9 different frequencies here, 7 of them with polarization. And the galactic dust emission is brightest in this, the highest frequency polarized channel that Planck had. So looking at those Planck maps here and comparing them with the BICEP and Keck maps, these Planck maps are made at higher frequencies. They're made across the whole sky, so we're just zooming into a small patch of sky here. And the sensitivity of Planck is quite limited when you look at a small patch of sky. So these much, much brighter fluctuations in the Planck map are really dominated by the noise, by the uncertainty in the Planck map, and also by the dust. The CMB signals that we detect here with BICEP are much, much fainter than these signals. So changing the color scales so that we can compare the patterns on a more equal footing, you can see the BICEP 2 B-mode pattern and this pattern here from Planck, which is a combination of noise and perhaps galactic dust. The question is how much of this B-mode pattern is in common between these two maps, and that indicates how strong the dust is. And it's not something you can easily do by looking at these maps by eye. You need to do a sophisticated analysis. And so the results of that analysis are shown here. And that ellipse that previously stretched through this whole region has now collapsed to some extent. And you can see it's collapsed, indicating that the dust amplitude is actually quite significant. That dust is definitely much greater than 0, and the preferred values of R have gone down correspondingly. And in fact, these models along this axis here, at R equals 0, no gravitational waves, are not ruled out. We cannot say from this analysis that there is significant evidence that R is greater than 0. We can say that it peaks at a value that R equals 0.05, and that R equals 0 and R equals 0.1 are at equal probability. But you get a result that looks like this about 8% of the time when there are no gravitational waves. And so to go further than this and narrow the uncertainties, we still need better data. Because these uncertainties, the ability to distinguish now between the CMB contribution to our B modes and the galactic dust, are limited by how deep the multi-frequency maps are that we have. And so the limitation right now is the signal-to-noise of the Planck maps. The black points here are the CMB contribution. The green points are our best estimate of the dust contribution to the B-mode spectrum. And to better separate these, the path forward is more sensitive maps at different colors. And also, ultimately, a removal of this lensing signal, which is quite bright compared to the signals that we are now trying to probe. So you can see now that these black points, showing only the CMB portion of the signal, they lie a bit above the line that would be for only lensing in CMB, indicating that there might be some excess there, but not significantly above that. So there is no significant evidence for an excess. It's consistent with this line here that would be inflationary gravitational waves at R of 0.05, but also consistent with much lower levels, R of 0.01 or even R of 0. And to do better, we need more sensitive data. And that data is coming. So that is what is so exciting about this field right now, is that in the next few years, efforts by our team and by many other teams that are working around the world are going to continue to narrow these uncertainties and continue to probe levels of inflationary gravitational waves that are in this key range here, R of 0.1 down to R of 0.001. And we expect that if we don't detect inflationary gravitational waves within the next 8 or 10 years, we will reach that level of a ratio of inflationary gravitational waves, 0.001, 1/1000th of the density fluctuations. And if we haven't seen gravitational waves from inflation at that point, we can rule out a broad class of inflationary models that happen at energy scales that are close to the scales expected for grand unified theories. Inflationary models that typically require the physics of inflation to involve a movement that is large compared to a fundamental constant that is related to quantum mechanics, the Planck constant, and gravity. And whether that is possible or not physically is an open question, and it's a critical question. We don't know whether that so-called Lithe bound formed by the Planck mass represents a fundamental limit on physics, like the speed of light. It would probably not be a hard limit, as the speed of light is, or whether it's a natural thing to evade. So there's a fundamental issue of physics at stake here in probing this class of inflationary models. And if we get to the end of this and we haven't detected any gravitational waves, inflation could still be true, but it would have to happen at lower energies and at later times. So the search for B modes today is very vibrant and ongoing, and our own team has BICEP 3 working at South Pole this year at a new color, a new frequency, and Keck array is now operating at 3 different colors. And we can expect the uncertainty on this parameter R to be cut in half by the data that we've taken just through the end of this year. So progress is very rapid in this field. And there are many other experiments that are also working very hard in this regard. So here I've highlighted just a selection of some of the competition. And it must be noted that these experiments all take complementary approaches with different beam sizes, different frequencies, different strategies that will make it most powerful for us to continue this search by combining all of this data together. And that, I think, is going to be the trend for the future. And I think it looks very promising. So here I should just note that one of these experiments, the Quixote experiment, is a Spanish effort. And it's particularly complementary because it works at low frequencies and could bring information on galactic foregrounds, the radio emission, to very high precision to this search. So we're very excited about that experiment. So these are exciting times that we live in, times where we can expect there to be rapid progress over the next few years on these fundamental questions that we're asking. So I'll stop there, and thank you very much for your attention.